Quantum mechanics is one of the most fascinating and bewildering fields of study in modern physics. At its heart, it challenges the very foundation of how we perceive reality, shifting from the certainties of classical physics to the unpredictable nature of subatomic particles. One of the key aspects of quantum mechanics that revolutionized our understanding of the universe was the introduction of the uncertainty principle by Werner Heisenberg. This principle brought with it a wave of change in both theoretical physics and philosophical inquiry. It fundamentally altered our view of the universe, showing that at the smallest scales of matter, there is no absolute certainty. Rather, uncertainty is an inherent feature of the natural world. In the world of classical physics, dating back to the days of Newton and Galileo, the laws of motion and gravitation were seen as absolute. These laws offered a predictable, deterministic view of the universe. Given the position, mass, and velocity of an object, one could predict its future state with great precision. If one could know every factor about a system, its future could be determined with certainty. For example, when you throw a ball in the air, you can calculate its trajectory, speed, and time of flight with great accuracy. This notion of predictability was the backbone of classical science. But this perspective began to unravel in the early 20th century as scientists delved into the world of atoms and subatomic particles. Classical physics struggled to explain the behavior of particles at the atomic level, where things seemed to operate in a completely different manner. Instead of behaving in predictable ways, particles at this level exhibited strange, seemingly random behavior that was completely at odds with the deterministic principles of classical mechanics. As scientists began exploring the world of quantum physics, they encountered phenomena that couldn't be explained by the classical rules of the universe. It was in the midst of these discoveries that Werner Heisenberg, in 1927, introduced his uncertainty principle. Heisenberg, one of the founding figures of quantum mechanics, proposed that there is a fundamental limit to how precisely we can measure certain pairs of properties of a particle. The most famous pair of properties involved is the position and momentum of a particle. The uncertainty principle states that the more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. This was not a limitation of the tools available at the time, but a fundamental characteristic of nature. Heisenberg's principle brought with it a shocking realization. At the atomic and subatomic levels, nature does not behave in a perfectly predictable manner. Before Heisenberg's groundbreaking work, the prevailing thought was that if we could know enough about a particle's position and momentum, we could predict its future behavior. Classical physics was built on this assumption. However, Heisenberg's uncertainty principle disrupted this concept. It forced scientists to acknowledge that there are limits to the precision with which we can measure a system, and more importantly, that these limits are inherent to the nature of reality itself. At first, Heisenberg's idea was met with skepticism. It was a difficult concept to grasp, especially because it contradicted centuries of established thought. However, as experiments in quantum mechanics continued to unfold, the uncertainty principle gained widespread acceptance. One of the key reasons for this was that the principle could be mathematically derived from the laws of quantum mechanics. In other words, the uncertainty was not just a philosophical idea but was supported by experimental data. This made the uncertainty principle one of the most important and revolutionary concepts in physics. The uncertainty principle has far-reaching implications beyond just the world of physics. It has sparked debates among philosophers, challenging the very nature of reality and the limits of human knowledge. Before Heisenberg, the general belief in science was that if one had enough information about a system, they could predict its behavior with certainty. But Heisenberg's principle shattered this belief. It suggested that the universe is fundamentally unpredictable and that there are limits to what we can know. This idea raises profound questions about the nature of existence. If we cannot predict the behavior of particles with absolute certainty, then what does that mean for our understanding of the world around us? What does it say about our ability to ever fully understand the universe? These philosophical questions are not just academic, they challenge our basic assumptions about reality. For centuries, human beings have strived for certainty and control over the world around them. We've built civilizations on the belief that with enough knowledge, we can shape our future and control our environment. But Heisenberg's uncertainty principle introduced a level of humility into our worldview. It forced us to accept that there are limits to our knowledge, and that the universe is far more complex and mysterious than we had ever imagined. The implications of the uncertainty principle extend beyond just philosophy. It also has practical consequences in modern physics. Quantum mechanics, which is based on the principles introduced by Heisenberg and others, has led to the development of technologies that we now use in everyday life, from semiconductors and computers to lasers and medical treatments. The unpredictability of quantum particles is not just a theoretical curiosity, but is at the heart of technologies that power much of our modern world. This is an important reminder that even the most abstract and seemingly esoteric principles of physics can lead to tangible advancements in technology. But the uncertainty principle also raises important questions about the very nature of measurement and observation. In classical physics, measurements were thought to be objective. That is, the act of measuring something did not influence the outcome. However, quantum mechanics, as described by Heisenberg's principle, suggests that observation plays a crucial role in determining the state of a system. In the quantum world, particles exist in a state of probability until they are observed or measured. This has led to one of the most famous thought experiments in physics, Schrödinger's cat. In this experiment, a cat is placed in a box with a radioactive atom that may decay and release poison. According to quantum mechanics, until the box is opened, the cat is both alive and dead, existing in a superposition of states. This paradox illustrates the strange and counterintuitive nature of quantum mechanics and the profound effect that observation has on reality. Heisenberg's uncertainty principle, in many ways, represents the heart of the quantum revolution. It marks the transition from the clear-cut, deterministic world of classical physics to the unpredictable and probabilistic world of quantum mechanics. The principle upends our traditional view of the universe, revealing that certainty is not always possible. It reminds us that the world at the smallest scales operates in ways that are fundamentally different from our everyday experiences. And, just as importantly, it forces us to acknowledge that there are limits to our knowledge, no matter how advanced our technology becomes. The shift from certainty to uncertainty is not just a change in physics, but a profound transformation in how we understand the universe. It invites us to reconsider the nature of reality and our place within it. Heisenberg's uncertainty principle remains one of the cornerstones of modern physics and continues to challenge both scientists and philosophers alike. While it may seem counterintuitive, the principle opens up a world of possibilities, where uncertainty is not a weakness but a defining feature of the universe. The discovery that uncertainty is built into the very fabric of reality forces us to confront the unknown and embrace the mysteries that lie at the heart of existence. Heisenberg's uncertainty principle not only transformed physics, but also had a profound impact on our philosophical understanding of the universe. The principle's implications extend far beyond the realm of science, forcing us to reconsider the very fabric of reality. To understand the full significance of Heisenberg's work, it is essential to explore its consequences on various fields and the ongoing debates it has sparked about the nature of knowledge, measurement, and the limitations of human understanding. The uncertainty principle suggests that reality, at its core, is inherently probabilistic rather than deterministic. In classical physics, it was assumed that the future could be predicted with certainty given complete knowledge of a system's present state. Newtonian physics operated on the premise that everything, from the motion of planets to the trajectory of a thrown ball, could be understood and predicted precisely. The exact position and velocity of an object could be known at any given moment, and, in theory, its future could be calculated with great accuracy. This view of a predictable, deterministic universe worked for most everyday phenomena. However, the quantum world, as described by Heisenberg, presented a stark contrast to this worldview. The uncertainty principle states that there are fundamental limits to the precision with which we can simultaneously know certain pairs of properties of a particle, most notably its position and momentum. The more accurately we measure one of these properties, the less accurately we can measure the other. This is not due to flaws in measurement tools or human error, but a natural limit intrinsic to the way the universe operates at microscopic scales. In other words, the universe is not inherently predictable, and the very act of measurement alters the system. This insight into the probabilistic nature of quantum mechanics raised profound questions about the nature of reality itself. Before Heisenberg, the dominant worldview in science was rooted in a belief in an objective reality that existed independently of the observer. The classical view held that the universe operated according to fixed laws of motion that were independent of our observation or knowledge of them. The laws of physics were thought to describe an objective reality that would remain unchanged regardless of whether or not we observed it. However, the uncertainty principle introduced the idea that the act of observing a system could fundamentally change it, challenging the notion of an objective reality that exists independent of our perception. This led to a fundamental philosophical shift. In quantum mechanics, particles do not exist in a specific state until they are observed or measured. Instead, they exist in a state of probability with various possible outcomes until an observation collapses these possibilities into one reality. This principle, known as wave function collapse, suggests that the observer plays an integral role in the creation of reality at the quantum level. This is in stark contrast to the classical view, where the observer was thought to be a passive entity that merely observed the world without influencing it. One of the most famous thought experiments to illustrate this quantum reality is Schrödinger's cat. In this thought experiment, a cat is placed in a box with a radioactive atom that may or may not decay. If the atom decays, the cat is killed by the release of poison. If it doesn't decay, the cat remains alive. According to quantum mechanics, until the box is opened and the cat is observed, it is in a superposition of both alive and dead states. It is only the act of observation that forces the cat into one of the two definite states. This paradox illustrates the counterintuitive nature of quantum mechanics and the idea that reality, at the quantum level, is not fixed until observed. Schrödinger's cat thought experiment was designed to show the absurdity of this interpretation when applied to everyday objects. While it is possible to imagine subatomic particles existing in superposition, the idea of macroscopic objects, like a cat, existing in multiple states at once seems nonsensical. Nevertheless, the philosophical implications are clear. Quantum mechanics challenges the very nature of reality. The uncertainty principle, along with the concept of wave function collapse, forces us to question whether the world we perceive is truly objective or whether it exists only in relation to our perception of it. Are we the creators of the reality we observe, or do we merely uncover it as it is? This question extends to the role of the observer. In classical physics, the observer was thought to be external to the system, unaffected by it. But in the quantum world, the observer is integral to the outcome. The uncertainty principle implies that the mere act of measurement affects the system being measured. This is not a limitation of our instruments, but a fundamental feature of nature. The implications of this idea are still being debated. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, argue that particles do not have definite properties until they are measured, while others, like the many worlds interpretation, proposed that all possible outcomes occur in parallel worlds. The philosophical implications of the uncertainty principle have inspired a wide range of interpretations and schools of thought. In the early 20th century, physicists such as Niels Bohr and Albert Einstein engaged in heated debates over the nature of reality in light of quantum mechanics. Einstein, who famously remarked that God does not play dice with the universe, was uncomfortable with the idea that the universe operated according to probability. He preferred a deterministic view, where the future could be known with certainty if enough information was available. Bohr, on the other hand, embraced the probabilistic nature of quantum mechanics, arguing that uncertainty was not a flaw but a fundamental feature of the natural world. In the years since these debates, the uncertainty principle has become a cornerstone of modern physics, with far-reaching implications in both theory and technology. Heisenberg's work paved the way for further developments in quantum mechanics, including quantum field theory and quantum computing. These fields continue to expand our understanding of the universe and have led to breakthroughs in technology, from the creation of semiconductors to advancements in medical imaging. Quantum mechanics is now integral to much of the technology we use every day, even though its implications still baffle our intuitions. Heisenberg's uncertainty principle also sparked a shift in how we understand knowledge itself. For centuries, the goal of science was to achieve complete understanding and predictability. Heisenberg's principle, however, introduced the idea that there are limits to what we can know. This realization challenges the very notion of omniscient knowledge. No matter how advanced our technology becomes, there will always be an inherent uncertainty in our understanding of the world at the quantum level. This has profound implications for how we approach not only science, but also the limits of human knowledge. In conclusion, Heisenberg's uncertainty principle represents a fundamental shift in how we understand the universe. It reveals that uncertainty, rather than certainty, is the true nature of reality at the quantum level. This realization has profound philosophical implications, challenging our understanding of the role of the observer, the objectivity of reality, and the limits of human knowledge. It also opened the door to an entirely new way of understanding the universe, one that is still evolving today. While the uncertainty principle may seem counterintuitive, it has become a cornerstone of modern physics, influencing both our theoretical understanding of the universe and the technologies that shape our world. It has reminded us that, at the most fundamental level, the universe is far more complex and mysterious than we ever imagined. The uncertainty principle, introduced by Werner Heisenberg in 1927, is one of the most profound and influential concepts in quantum mechanics. This principle challenges the classical view of the universe by asserting that certain pairs of physical properties, such as position and momentum, cannot both be known to arbitrary precision at the same time. The more accurately one of these properties is measured, the less precisely the other can be determined. This idea revolutionized our understanding of the microcosm of the universe, revealing that at the quantum level, uncertainty is an intrinsic feature of nature, not a limitation of measurement tools. Before delving into the full significance of Heisenberg's uncertainty principle, it is essential to understand the background against which it emerged. Classical physics, which governed the laws of motion and gravitation, was rooted in a deterministic worldview. According to classical mechanics, if one could know the initial conditions of a system, its position, velocity, and other factors, one could predict the future behavior of that system with absolute certainty. This deterministic outlook gave rise to the belief that the universe, at its core, was predictable and orderly. Newton's laws of motion, for example, allowed scientists to forecast the path of a moving object with great precision. The world appeared to be governed by an underlying set of laws that, once understood, could be applied universally. However, the advent of quantum mechanics shattered this view of the universe. As physicists began exploring the atomic and subatomic worlds, They found that particles did not behave in the predictable, ordered manner described by classical mechanics. Instead, they exhibited behaviors that were fundamentally random and uncertain. This realization came as a shock to the scientific community, which had long believed in the reliability of classical physics. At the heart of quantum mechanics lay the concept of wave-particle duality, which proposed that particles such as electrons could exhibit both wave-like and particle-like behavior. This duality meant that particles could not be pinned down to a specific location or velocity at any given time. It was within this context that Heisenberg introduced the uncertainty principle. His groundbreaking work in quantum mechanics led him to the conclusion that the very act of measuring a particle's properties, such as its position or momentum, introduced an inherent uncertainty into the system. This was not because of limitations in experimental technology or human error, but because of the nature of reality itself. In classical mechanics, one could measure the position and momentum of an object simultaneously and with great precision. But in quantum mechanics, these two properties were fundamentally linked in such a way that measuring one with precision made it impossible to measure the other with the same level of accuracy. Heisenberg's uncertainty principle marked a departure from classical physics in that it introduced the concept of limits on knowledge. While classical physics assumed that the universe could be fully understood if one had complete knowledge of a system, quantum mechanics suggested that some aspects of reality are fundamentally unknowable. This was a profound shift in how scientists thought about the world, and it forced them to confront the possibility that reality at the atomic level might not conform to the laws of certainty that had governed the macroscopic world for centuries. The uncertainty principle has profound implications not only for physics, but also for our understanding of reality itself. One of the most striking consequences of the principle is that it challenges the classical notion of an objective reality that exists independently of the observer. In classical physics, the observer was thought to be a passive entity, able to observe the world without influencing it. The laws of physics were assumed to describe an objective reality that would remain unchanged regardless of whether or not anyone was observing it. In contrast, Heisenberg's principle suggests that the very act of measurement changes the system being observed. In the quantum world, particles do not have definite properties until they are observed or measured. Instead, they exist in a state of probability, with multiple possible outcomes, until an observation collapses the wave function into one definite state. This introduces a new layer of subjectivity to our understanding of reality. This idea has led to intense philosophical debates about the nature of reality and the role of the observer. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, argue that particles do not have definite properties until they are measured, implying that reality is, in some sense, created by the act of observation. This interpretation challenges the classical view that the universe exists independently of our perception of it. Other interpretations, such as the many worlds theory, propose that all possible outcomes of a quantum event occur in parallel universes, with each possibility manifesting in a different reality. These debates have profound implications for our understanding of the universe and our place within it, forcing us to reconsider the limits of human knowledge and the nature of objective reality. Another important consequence of the uncertainty principle is its impact on the determinism of the universe. Before Heisenberg, the prevailing view in science was that the universe was deterministic, meaning that if one had complete knowledge of the present, one could predict the future with certainty. Classical mechanics was built on this assumption, and it worked well for most macroscopic systems. However, Heisenberg's uncertainty principle shattered this deterministic view of the universe. According to quantum mechanics, even if we knew the position and momentum of a particle, we could not predict its future behavior with certainty. This randomness at the quantum level challenges our understanding of causality and raises important questions about the nature of time and the limits of prediction. The uncertainty principle also has profound implications for the concept of measurement itself. In classical physics, measurements were assumed to be objective and external to the system being measured. The measurement of a particle's position, for example, was thought to provide an accurate snapshot of the particle's state at a particular moment in time. However, in quantum mechanics, the very act of measuring a particle's position or momentum alters the system being measured. This has led to the development of the concept of wave function collapse, which proposes that a particle's wave function, describing all of its possible states, collapses into a definite state when it is measured. This introduces a new layer of complexity to our understanding of measurement, suggesting that measurement itself is an active process that influences the outcome. As the implications of the uncertainty principle became more widely understood, it led to significant advancements in quantum theory. The principle laid the foundation for quantum field theory, which describes the behavior of fields and particles at the quantum level. It also paved the way for the development of quantum computing, which harnesses the probabilistic nature of quantum mechanics to perform computations far faster than classical computers. Today, the uncertainty principle remains one of the cornerstones of quantum mechanics and continues to shape our understanding of the microcosm of the universe. Despite its profound impact on our understanding of physics, the uncertainty principle has not been without controversy. Some physicists, such as Albert Einstein, were uncomfortable with the idea of inherent randomness in the universe. Einstein famously remarked, "God does not play dice with the universe," expressing his belief in the determinism of the cosmos. However, experiments in quantum mechanics have consistently supported the probabilistic nature of particles, leading most physicists to accept the uncertainty principle as a fundamental feature of nature. The uncertainty principle also has important practical applications. It has led to the development of technologies such as semiconductors, lasers, and quantum computers. These technologies rely on the principles of quantum mechanics and the probabilistic behavior of particles. While the uncertainty principle may seem abstract and counterintuitive, its consequences are far-reaching and continue to shape the technological landscape. In conclusion, Heisenberg's uncertainty principle is one of the most groundbreaking and transformative ideas in the history of science. It challenges our classical notions of determinism, measurement, and reality itself. By introducing the idea that there are limits to our knowledge and that uncertainty is an inherent feature of nature, Heisenberg reshaped the way we understand the universe. The uncertainty principle not only revolutionized physics but also raised profound philosophical questions about the nature of reality and the role of the observer. It remains a cornerstone of quantum mechanics, continuing to shape our understanding of the world at the smallest scales. Heisenberg's uncertainty principle not only marked a major shift in physics, but also revolutionized our understanding of the world at its most fundamental level. This principle, which challenges the classical notion of determinism and predictability, brings with it profound philosophical implications. By establishing that uncertainty is an intrinsic feature of reality, Heisenberg's work has had lasting consequences for how we think about the nature of knowledge, the limits of human perception, and the structure of the universe. This exploration into uncertainty reaches beyond just theoretical physics, stretching into the realms of philosophy, technology, and our overall conception of the cosmos. The philosophical questions raised by Heisenberg's uncertainty principle are among the most profound in modern science. Before Heisenberg, the dominant paradigm in both philosophy and physics was that the universe was deterministic, meaning that if we knew enough about the current state of a system, we could predict its future with absolute certainty. This deterministic worldview had its roots in classical mechanics, where everything from the motion of planets to the trajectory of everyday objects was considered predictable with sufficient information. In classical physics, if one knew a particle's exact position and momentum, one could foresee its future behavior. However, Heisenberg's uncertainty principle revealed that, at the subatomic level, things were radically different. The uncertainty principle states that certain pairs of properties, like position and momentum, cannot be measured simultaneously with arbitrary precision. The more precisely we measure one of these properties, the less accurately we can know the other. This revelation contradicted centuries of thought and suggested that the very fabric of reality was not deterministic at all, but probabilistic. Instead of being able to predict the future with certainty, quantum mechanics tells us that only probabilities can be assigned to events, and those probabilities are governed by mathematical rules rather than hard and fast certainties. This shift in thinking also has significant implications for the concept of causality. Classical physics operates under the assumption of causality, where every event has a specific cause, and the future is determined by the past. In contrast, quantum mechanics, with its probabilistic nature, introduces a new level of uncertainty into the relationship between cause and effect. While the laws of classical mechanics are deterministic, quantum mechanics asserts that, at least at the subatomic level, the future is not fully determined by the past. The behavior of quantum particles can be understood in terms of probabilities rather than certainties, meaning that causality, as traditionally understood, may not apply at the quantum level. The probabilistic nature of quantum mechanics, as revealed by Heisenberg, also challenges our traditional ideas about the nature of reality. In classical physics, the world was seen as an objective entity that existed independently of our perception of it. The physical world, governed by laws like those of motion, was assumed to exist in a fixed state, whether or not we were observing it. However, Heisenberg's uncertainty principle forced a reconsideration of this view. In the quantum world, particles do not have well-defined properties until they are observed or measured. Instead, they exist in a state of probability where different outcomes exist simultaneously, and it is only when we make a measurement that these possibilities collapse into one reality. This has led to new philosophical questions about the role of the observer in shaping reality. If reality exists only when observed, then what does that say about the objective nature of the universe? Is reality a product of our perception, or does it exist independently of us? This concept is encapsulated in the famous thought experiment known as Schrödinger's cat. Schrödinger proposed a scenario in which a cat is placed in a sealed box with a radioactive atom that may or may not decay. If the atom decays, the cat dies. If it does not, the cat remains alive. According to the Copenhagen interpretation of quantum mechanics, the cat is simultaneously alive and dead until the box is opened and the cat is observed. The act of observation collapses the wave function, forcing the cat into one definite state. This paradox illustrates the strange nature of quantum reality and highlights the idea that, in quantum mechanics, particles and even macroscopic objects like a cat can exist in multiple states at once, existing in a superposition of possibilities until observed. This challenges the classical notion of an objective reality that exists independently of observation and forces us to consider the possibility that the observer plays a role in shaping what we perceive as reality. Heisenberg's uncertainty principle also led to a major rethinking of measurement itself. In classical physics, measurements were assumed to be objective. The act of measuring a system, whether it was the position of a ball or the velocity of a moving object, was seen as external to the system itself. Measurement did not alter the system. It merely provided information about it. In quantum mechanics, however, the uncertainty principle tells us that measurement is not a passive activity. The act of measuring a system, whether it's the position or momentum of a particle, affects the system in such a way that the very properties being measured are altered. This idea introduces an active role for the observer, which is not just limited to human observers but extends to any interaction with the system. This dynamic interaction between the observer and the system complicates our traditional understanding of measurement and raises important questions about the role of observation in quantum systems. Furthermore, Heisenberg's uncertainty principle has profound consequences for our understanding of knowledge itself. For centuries, the goal of science has been to gain complete knowledge of the universe, and with enough knowledge to predict and control its future. The uncertainty principle, however, introduces the idea that there are fundamental limits to our knowledge. Even with the most advanced instruments and methods, we cannot know certain pairs of properties with absolute precision. This challenges the ideal of complete knowledge and forces us to acknowledge that uncertainty is built into the fabric of the universe. This realization has led some philosophers and physicists to reconsider the idea of objective knowledge. If we cannot know the complete state of a system, then how can we claim to have true knowledge of the world? Does knowledge become less about certainty and more about understanding the probabilities that govern the universe? As Heisenberg's uncertainty principle became more widely accepted, it set the stage for the development of further quantum theories, including quantum field theory, quantum electrodynamics, and quantum computing. These areas of study have opened up new frontiers in our understanding of the universe and have led to technological advances that were unimaginable in Heisenberg's time. The uncertainty principle has contributed to the development of technologies such as lasers, transistors, and magnetic resonance imaging, MRI, all of which rely on principles derived from quantum mechanics. Despite the overwhelming evidence supporting the uncertainty principle, it remains a controversial and complex concept. Some physicists, notably Albert Einstein, were uncomfortable with the probabilistic nature of quantum mechanics. Einstein famously quipped, "God does not play dice with the universe," expressing his reluctance to accept the idea that randomness governs the universe. Einstein preferred a deterministic view of reality, where the laws of physics could fully determine the state of the universe. However, experiments and observations have consistently supported the probabilistic nature of quantum systems, and the uncertainty principle remains one of the cornerstones of quantum theory. Today, the uncertainty principle is not just a theoretical curiosity, but a fundamental part of our understanding of the universe. It has paved the way for advances in quantum technology, including quantum computers, which have the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science. Quantum mechanics, with its inherent uncertainty, continues to shape the future of science and technology, even as it continues to challenge our deepest philosophical assumptions. In conclusion, Heisenberg's uncertainty principle has had far-reaching implications for both physics and philosophy. By introducing the idea that uncertainty is a fundamental characteristic of nature, Heisenberg's work shattered the classical worldview of a deterministic, predictable universe. It forced us to confront the limits of human knowledge, the role of the observer in shaping reality, and the nature of the universe at its most fundamental level. The uncertainty principle remains one of the most profound and revolutionary concepts in the history of science, and its implications continue to shape our understanding of the world and the technologies that drive our modern world. Heisenberg's uncertainty principle, introduced in 1927, stands as one of the cornerstones of quantum mechanics, altering the landscape of physics forever. The principle, proposed by Werner Heisenberg, asserts that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision simultaneously. This idea shattered the classical, deterministic view of the universe, which had been the foundation of physics for centuries. The implications of this principle go beyond mere theoretical physics, challenging our understanding of reality itself and altering our fundamental perception of the universe. At its core, the uncertainty principle tells us that the more precisely we try to measure one of these properties, the less accurately we can measure the other. For example, if we measure the position of a particle with great precision, its momentum becomes more uncertain, and vice versa. This principle is not a result of imperfect instruments or human error, but rather an intrinsic property of nature itself. Before Heisenberg's work, the classical worldview was rooted in the belief that if we knew the present state of a system, we could predict its future with absolute certainty. This deterministic view, inherited from the work of Isaac Newton and classical physics, stated that the universe operated like a well-oiled machine, where, given enough information, everything could be understood and predicted. The challenge to this deterministic worldview came with the birth of quantum mechanics, a field that emerged in the early 20th century to explain phenomena that could not be accounted for by classical physics. Quantum mechanics was built on the realization that particles at the atomic and subatomic levels behave in ways that classical mechanics could not explain. The particles did not follow precise trajectories, and their behavior seemed to be governed by probabilities rather than certainties. The idea that the position and momentum of a particle could be known exactly at the same time contradicted the reality that quantum mechanics revealed. This is where Heisenberg's uncertainty principle stepped in, forever changing our understanding of nature. Heisenberg's work brought to light the notion that the universe, at the smallest scales, was inherently uncertain. This uncertainty was not just a limitation of our ability to measure things, but a reflection of the way reality itself worked. At the quantum level, particles do not have definite positions and velocities until they are observed. Before observation, particles exist in a superposition of possible states. This was a radical departure from classical physics, where objects were assumed to exist in a specific state, independent of observation. The implications of Heisenberg's uncertainty principle were not just technical, they were philosophical, questioning the very nature of reality and our ability to understand it. One of the most significant consequences of the uncertainty principle is that it challenges the concept of determinism. In classical physics, determinism reigned supreme. It was believed that, given enough information about a system's current state, its future could be predicted with complete certainty. This was the very foundation of classical mechanics. The trajectories of planets in the solar system, the motion of a thrown ball, and the behavior of everyday objects were all assumed to be completely predictable. The universe operated like a machine, and if you knew the position and velocity of every particle, you could calculate its future behavior with perfect accuracy. However, Heisenberg's principle shattered this assumption at the atomic and subatomic level. In the quantum world, certainty gave way to probability. Heisenberg's work revealed that the more precisely we measure a particle's position, the less certain we can be about its momentum. This probabilistic nature of particles is governed by the mathematical framework of quantum mechanics, where probabilities describe the likelihood of a particle's position or momentum at a given time. The idea of determinism, which had been so central to classical physics, no longer applied in the quantum world. The behavior of particles could only be understood in terms of probabilities, not certainties. This shift from determinism to probability has profound implications for how we view the universe. It suggests that, at its most fundamental level, the universe is not a predictable machine but a probabilistic system governed by the rules of chance. This realization challenged centuries of thought and raised important questions about the nature of reality. If the future is not determined by the present, what does that mean for our understanding of causality? How can we reconcile the seemingly random behavior of quantum particles with our everyday experience of cause and effect? Beyond its impact on determinism, the uncertainty principle also altered our understanding of measurement and observation. In classical physics, the observer was thought to be external to the system, unaffected by it. When you measure the position of a ball, for example, the act of measuring does not change the ball's position. In quantum mechanics, however, the situation is different. The uncertainty principle suggests that the very act of measurement alters the state of the system being measured. This is not just a consequence of human error or imperfect instruments, but an intrinsic feature of nature at the quantum level. The observer's role in quantum mechanics has led to a number of philosophical questions. One of the most famous thought experiments related to this is Schrödinger's cat. In this experiment, a cat is placed in a box with a radioactive atom that may or may not decay. If the atom decays, the cat dies. If it doesn't decay, the cat stays alive. According to quantum mechanics, the atom's decay is not determined until it is measured, so until the box is opened, the cat is in a superposition of both alive and dead states. The act of observation collapses this superposition into one definite state. This paradox demonstrates how, in the quantum world, observation plays a key role in shaping reality. The observer is no longer a passive participant in the measurement process, but an active one, influencing the system being measured. This concept of measurement and observation in quantum mechanics has led to different interpretations of quantum theory. The Copenhagen interpretation, for example, suggests that the wave function, which describes the probabilities of a particle's state, collapses into a single, definite outcome upon measurement. Other interpretations, such as the many worlds theory, propose that all possible outcomes of a quantum event occur in parallel worlds, with each possibility manifesting in a separate universe. These debates illustrate the complexity and depth of the philosophical implications of the uncertainty principle. While the uncertainty principle introduced a new way of understanding the universe, it also raised important questions about the limits of human knowledge. In classical physics, the goal of science was to achieve complete knowledge and understanding of the universe. With enough information, scientists believed, they could predict the future and control the forces of nature. The uncertainty principle, however, introduced the idea that there are fundamental limits to what we can know. No matter how advanced our instruments become, there will always be a degree of uncertainty in our measurements. This realization has profound implications for the pursuit of knowledge. It suggests that science may never be able to provide a complete and deterministic understanding of the universe, especially at the quantum level. This shift in thinking has led to a re-examination of the role of science and knowledge in human life. If uncertainty is built into the fabric of the universe, how should we approach the quest for understanding? Is knowledge always incomplete? And is it possible that there are things we will never be able to know or predict? These questions challenge not only scientists but also philosophers who have long pondered the nature of knowledge and the limits of human understanding. Heisenberg's uncertainty principle also has practical applications that have had a significant impact on technology. While the principle may seem abstract and theoretical, its consequences are deeply embedded in the technologies we use today. Quantum mechanics, and the uncertainty principle in particular, have paved the way for advances in fields such as quantum computing, cryptography, and telecommunications. These fields rely on the principles of quantum mechanics and the probabilistic behavior of particles to develop technologies that are far more powerful and efficient than anything classical physics could provide. For example, quantum computers harness the uncertainty inherent in quantum systems to process information in ways that classical computers cannot. The uncertainty principle, once seen as a strange and puzzling feature of the quantum world, has become the foundation for some of the most exciting technological advancements in modern science. In conclusion, Heisenberg's uncertainty principle has had a profound and lasting impact on both theoretical physics and our broader understanding of the universe. By revealing that uncertainty is an intrinsic feature of reality, Heisenberg shattered the deterministic worldview that had dominated classical physics for centuries. The principle not only changed our understanding of the microscopic world but also forced us to reconsider the nature of knowledge, measurement, and reality itself. As we continue to explore the implications of the uncertainty principle, we find that it shapes not only the theoretical landscape of quantum mechanics, but also the practical technologies that are transforming our world. The uncertainty principle remains one of the most important concepts in modern science, and its philosophical and technological consequences continue to unfold in new and exciting ways. The uncertainty principle, which was introduced by Werner Heisenberg in 1927, not only revolutionized quantum mechanics but also brought with it a profound shift in how we understand the fundamental workings of the universe. Heisenberg's principle, which suggests that certain pairs of physical properties of particles, such as position and momentum, cannot both be known to arbitrary precision at the same time, shattered the deterministic view of the universe that had been held for centuries. Instead, it revealed that uncertainty is an intrinsic feature of nature, fundamentally altering our understanding of reality itself. This principle's impact on science, philosophy, and technology continues to resonate today, making it one of the most significant contributions to modern physics. One of the most critical aspects of the uncertainty principle is the way it challenges classical physics. Classical physics, based on the work of Isaac Newton and others, was grounded in determinism. Determinism held that if we had complete knowledge of the current state of a system, we could predict its future behavior with certainty. This view applied to both macroscopic objects, like planets and cars, and smaller systems, such as atoms. In this classical view, the universe was considered a giant machine governed by laws of motion that, if fully understood, would allow us to predict everything about the future. Newton's laws of motion, for example, are deterministic, meaning that if we know the position and velocity of a moving object, we can calculate its future motion with absolute precision. However, this deterministic view of the universe began to break down when scientists started to probe the atomic and subatomic worlds. In these realms, the classical rules no longer seemed to apply. The behavior of particles, such as electrons, could not be described by the same deterministic equations that governed the motion of planets. Quantum mechanics, the new field of physics that emerged in the early 20th century, provided a framework to describe the bizarre behavior of these subatomic particles. Heisenberg's uncertainty principle was central to this new understanding of the universe, challenging the idea that we could ever fully know or predict the properties of particles at the quantum level. Heisenberg's uncertainty principle tells us that at the quantum level, we cannot know both the position and momentum of a particle with arbitrary precision. The more accurately we try to measure one of these properties, the less accurately we can measure the other. This is not due to limitations in our measurement tools or human error, but because of the inherent uncertainty that exists at the quantum scale. For instance, if we measure the position of an electron very precisely, its momentum becomes highly uncertain, and if we measure its momentum precisely, its position becomes uncertain. This relationship between position and momentum is not just a theoretical concept but a real, fundamental feature of the universe. The uncertainty principle, therefore, forced physicists to abandon the classical view that the universe was entirely deterministic and predictable. It introduced the idea that at the microscopic level, reality behaves probabilistically. Instead of being able to precisely calculate the future state of a system, quantum mechanics tells us that the best we can do is describe the probability of finding a particle in a particular state. This marked a profound departure from the classical worldview and introduced the concept of inherent randomness into the fabric of reality. The future is not determined with certainty, but is shaped by probabilities. This shift from determinism to probability has profound philosophical implications. Before the advent of quantum mechanics, philosophers and scientists alike believed that the universe operated according to fixed, predictable laws. Classical mechanics provided a clear, deterministic view of reality, where the universe followed strict cause and effect relationships. However, Heisenberg's uncertainty principle, along with other findings in quantum mechanics, raised important questions about the very nature of reality. If the universe is probabilistic at its core, What does that mean for our understanding of causality, free will, and even the nature of existence itself? The uncertainty principle also prompted a rethinking of the role of the observer in science. In classical physics, the observer was thought to be separate from the system being observed. A scientist could measure the properties of an object without affecting its state, but in quantum mechanics, the observer plays an integral role in shaping the outcome of a measurement. According to the Copenhagen interpretation of quantum mechanics, particles do not have definite properties such as position or momentum until they are observed. Instead, particles exist in a superposition of states, with various possibilities existing at once. It is only when a measurement is made that the superposition collapses into a single state. This idea, though still a subject of debate, suggests that observation itself is not a passive act but actively determines the state of a system. This concept of the observer's role in quantum mechanics led to one of the most famous thought experiments in the history of physics, Schrödinger's cat. In this experiment, a cat is placed in a box with a radioactive atom that has a 50% chance of decaying. If the atom decays, the cat is killed by poison, and if it does not decay, the cat remains alive. According to quantum mechanics, the atom's decay is not determined until it is observed, and thus the cat is in a superposition of both alive and dead states until the box is opened. The act of observation causes the wave function to collapse into one of the two possible outcomes, alive or dead. Schrödinger's cat thought experiment highlights the strange and counterintuitive nature of quantum mechanics and raises important questions about the relationship between observation and reality. These ideas about the observer's role in quantum mechanics have led to numerous interpretations of quantum theory. The Copenhagen interpretation, which was developed by Niels Bohr and others, holds that the wave function collapses when a measurement is made and the system assumes a definite state. Other interpretations, such as the many worlds theory, suggest that all possible outcomes of a quantum event actually occur, each in a different parallel universe. These differing interpretations reflect the philosophical challenges posed by quantum mechanics, particularly the issue of whether reality exists independently of our observations or whether it is shaped by our perception. In addition to its philosophical implications, the uncertainty principle has had a significant impact on the development of technology. Although the concept of uncertainty may seem abstract and theoretical, it has laid the foundation for some of the most important technological advances of the 20th and 21st centuries. Quantum mechanics, and particularly the principles of uncertainty, have played a central role in the development of technologies like lasers, transistors, and semiconductors. These technologies rely on the principles of quantum mechanics to function, and they have revolutionized fields such as computing, telecommunications, and medicine. One of the most exciting applications of quantum mechanics is quantum computing. Unlike classical computers, which use bits to represent data as either 0 or 1, quantum computers use quantum bits, or qubits, which can represent both 0 and 1 simultaneously due to the principle of superposition. This allows quantum computers to process information much more efficiently than classical computers for certain types of problems. The uncertainty principle plays a key role in quantum computing as it underlies the probabilistic behavior of quantum systems. Quantum computing has the potential to revolutionize fields like cryptography, artificial intelligence, and optimization, making it one of the most exciting areas of research in modern science. The uncertainty principle also continues to shape the development of quantum technologies like quantum cryptography and quantum sensors. Quantum cryptography, which uses the principles of quantum mechanics to create unbreakable encryption methods, has the potential to revolutionize the security of digital communication. Quantum sensors, which take advantage of the sensitivity of quantum systems to small changes in their environment, could lead to breakthroughs in fields such as medical imaging and environmental monitoring. These technologies, which were once the stuff of science fiction, are now becoming a reality thanks to our growing understanding of the uncertainty principle and its implications for the quantum world. In conclusion, Heisenberg's uncertainty principle has had a profound impact on both theoretical physics and practical technology. By revealing the intrinsic uncertainty that governs the quantum world, Heisenberg's work challenged the deterministic view of the universe and introduced a probabilistic model of reality. The uncertainty principle raised fundamental philosophical questions about the nature of reality, the role of the observer, and the limits of human knowledge. It also laid the groundwork for groundbreaking technological advances, from quantum computers to quantum cryptography, that continue to shape our modern world. Although the uncertainty principle may be difficult to grasp, it remains one of the most important concepts in modern science, continuing to influence both our understanding of the universe and the technologies that drive our world forward. The uncertainty principle, introduced by Werner Heisenberg in 1927, is one of the most pivotal concepts in quantum mechanics. It challenges the very core of classical physics, which operated on the belief that if we knew enough about a system's current state, we could predict its future with absolute certainty. Heisenberg's principle, however, demonstrated that at the quantum level, certain pairs of physical properties, such as a particle's position and momentum, cannot be precisely measured at the same time. The more precisely we try to measure one property, the less precisely we can know the other. This profound insight not only altered our understanding of the microscopic world, but also prompted new philosophical questions about the nature of reality and the role of the observer. The first significant impact of the uncertainty principle is that it fundamentally challenges the deterministic worldview of classical physics. Before quantum mechanics, it was widely accepted that the universe operated in a predictable manner. Given the position and velocity of an object, classical physics held that its future could be predicted with absolute certainty. Newton's laws of motion, for example, were deterministic. They provided precise mathematical relationships that allowed scientists to calculate the future behavior of objects. However, Heisenberg's uncertainty principle upended this perspective by asserting that at the atomic and subatomic levels, certainty is not possible. Instead, particles exist in states of probability, and their behavior cannot be determined with the precision that classical physics promised. This transition from a deterministic to a probabilistic worldview was one of the most profound shifts in the history of science, reshaping our understanding of the fundamental laws that govern nature. Secondly, the uncertainty principle also introduced the idea that observation plays a crucial role in determining the state of a system. In classical physics, the observer was seen as a passive entity, unaffected by the system being measured. One could measure the position of an object without changing its state. However, in quantum mechanics, the act of measurement is not neutral. It affects the system being observed. According to Heisenberg, the more precisely we measure a particle's position, the less we can know about its momentum, and the very act of observing a particle collapses its wave function, forcing it to assume a definite state. This realization has led to the notion that, in quantum mechanics, the observer is not a detached bystander, but an active participant in shaping the system's outcome. This has profound implications for our understanding of reality, as it suggests that reality is not an objective entity existing independently of the observer, but rather something that is influenced by the act of observation itself. The third key impact of the uncertainty principle lies in its philosophical implications. Before the advent of quantum mechanics, the prevailing belief in science and philosophy was that the universe operated according to fixed, objective laws, and that the truths of the universe could be uncovered through measurement and observation. Heisenberg's principle, however, introduced the idea that there are limits to human knowledge. No matter how advanced our instruments become, there are fundamental limits to what we can know about the universe. This has profound implications for our understanding of knowledge itself. It suggests that, at least in the quantum realm, certainty is unattainable, and our understanding of the universe is inherently incomplete. This shift challenges the Enlightenment-era belief in the power of reason and measurement to uncover the ultimate truths about nature. It also raises questions about the nature of objective reality, and whether it is something independent of our perception or if it is in some ways shaped by our consciousness. Finally, the uncertainty principle has led to remarkable advancements in technology. While the principle itself may seem abstract and esoteric, its implications have had a profound impact on the development of modern technologies. Quantum mechanics, and by extension the uncertainty principle, has been the foundation for the development of technologies such as semiconductors, lasers, and medical imaging techniques. These innovations are all rooted in the probabilistic nature of quantum systems, which are governed by the same principles Heisenberg discovered. One of the most exciting developments in recent years has been the rise of quantum computing, a field that leverages the principles of quantum mechanics to perform computations far more efficiently than classical computers. Quantum computers rely on the idea of superposition, where qubits can exist in multiple states simultaneously, allowing them to process vast amounts of data at once. The uncertainty principle plays a crucial role in the operation of quantum computers, highlighting the ways in which the principle's impact extends beyond theoretical physics and into practical applications that are transforming industries like cryptography, artificial intelligence, and materials science. In summary, the uncertainty principle has fundamentally transformed our understanding of the universe. By challenging the deterministic worldview of classical physics, introducing the role of the observer in shaping reality, and raising profound philosophical questions about the nature of knowledge and objective reality, Heisenberg's principle has reshaped both science and philosophy. Furthermore, it has paved the way for a variety of technological advancements, ranging from semiconductors to quantum computing, that have had a profound impact on society. Despite its counterintuitive nature, the uncertainty principle remains one of the most important and influential concepts in modern science. The uncertainty principle, introduced by Werner Heisenberg in 1927, is one of the most transformative and fundamental concepts in the field of quantum mechanics. It states that certain pairs of physical properties, such as position and momentum, cannot both be measured with absolute precision at the same time. The more accurately one of these properties is measured, the less precisely the other can be known. This principle challenges the classical deterministic view of the universe, where it was once believed that, with enough knowledge, one could predict the future state of any system with complete certainty. Heisenberg's uncertainty principle, however, fundamentally altered this view, revealing that uncertainty is an intrinsic feature of nature at the quantum level. One of the most important implications of the uncertainty principle is its challenge to the deterministic worldview that dominated classical physics. Classical mechanics, based on the works of Newton, proposed that if we knew the exact position, velocity, and other properties of a particle, we could predict its future behavior with perfect accuracy. This assumption was at the heart of classical physics and was considered a cornerstone of the scientific understanding of the universe. However, Heisenberg's principle introduced a radical shift in this perspective. At the quantum level, particles do not behave in predictable ways. Instead, they exist in states of probability, governed by chance rather than certainty. The uncertainty in position and momentum is not a result of experimental limitations but is a fundamental property of nature. This revelation turned the classical view of a perfectly predictable universe on its head, introducing an element of randomness and probability that had never been considered before in scientific theory. The second key impact of the uncertainty principle is its influence on the concept of measurement and the role of the observer in quantum mechanics. In classical physics, measurements were assumed to be objective and external to the system being studied, a scientist could measure the position of an object without influencing its behavior. However, in quantum mechanics, the act of measurement is not neutral. The very process of observing or measuring a quantum system affects the system itself. This is not just a limitation of measurement tools, but a fundamental characteristic of the quantum world. When we measure the position of a particle, for example, we disturb its momentum, and vice versa. This inherent interaction between the observer and the observed challenges the classical idea of an objective reality, where the system and the observer are separate. In quantum mechanics, the observer plays an active role in shaping the outcome of the measurement, and this has profound implications for how we understand the relationship between observation, reality, and knowledge. The third key aspect of the uncertainty principle lies in its philosophical implications. Prior to Heisenberg's work, the dominant philosophical belief in both science and general thought was that the universe operated according to fixed laws, and that with enough information, humans could understand and predict its behavior. The uncertainty principle disrupted this certainty, introducing the idea that the universe, particularly at the quantum level, is fundamentally unknowable in its entirety. We can never have complete knowledge of a system's state. There will always be inherent uncertainty. This challenges long-held beliefs about the nature of knowledge, suggesting that some aspects of reality may always remain beyond our grasp. This has led to significant philosophical debates about the limits of human knowledge and our ability to understand the universe. It raises questions about whether reality exists independently of our perception, or if it is, in some sense, shaped by our observations and interactions with it. The fourth key point about the uncertainty principle is its impact on the concept of causality. In classical physics, causality was seen as a strict relationship. Every effect had a cause, and the future was determined by the past. This deterministic view of causality allowed scientists to predict the future behavior of a system if they knew its current state. However, the uncertainty principle introduces a probabilistic model of the universe. In the quantum world, events do not follow a strict cause and effect pattern. Instead, particles exist in a state of probability, and their behavior can only be described in terms of likelihoods. This randomness, at the quantum level, challenges the deterministic view of causality and raises important questions about the nature of cause and effect. If the behavior of particles is governed by probabilities, does this mean that causality, as traditionally understood, breaks down at the quantum level? Finally, the uncertainty principle has profound implications for the development of quantum technologies, particularly in the fields of quantum computing, cryptography, and telecommunications. Despite its abstract and counterintuitive nature, the principles of quantum mechanics, including the uncertainty principle, have led to groundbreaking technological advancements. Quantum computers, for example, leverage the probabilistic nature of quantum particles to perform computations much faster than classical computers. In quantum computing, qubits' quantum bits can exist in a superposition of states representing both 0 and 1 simultaneously. This enables quantum computers to solve complex problems much more efficiently than their classical counterparts. Quantum cryptography, which uses the principles of quantum mechanics to create secure communication channels, is another area where the uncertainty principle plays a key role. The uncertainty in quantum measurements makes it impossible for eavesdroppers to intercept information without disturbing the system, providing a level of security that classical encryption methods cannot match. These technologies are still in the early stages of development, but hold immense potential to revolutionize fields such as information security, artificial intelligence, and data processing. In conclusion, Heisenberg's uncertainty principle has had a profound impact on both the theoretical and practical aspects of science and technology. By challenging the classical notion of a deterministic universe, it introduced the concept of uncertainty and probability at the quantum level. The principle also revolutionized our understanding of measurement, suggesting that the act of observation plays an integral role in shaping the outcome of a quantum system. Moreover, it has had significant philosophical implications, forcing us to reconsider the nature of knowledge, causality, and reality itself. The uncertainty principle has also paved the way for numerous technological advancements, from quantum computing to quantum cryptography, that continue to shape the future of science and technology. Despite its counterintuitive nature, the uncertainty principle remains one of the most important and influential concepts in modern physics, continuing to challenge and inspire new ways of thinking about the universe. Heisenberg's uncertainty principle stands as one of the most groundbreaking concepts in modern physics, fundamentally challenging classical ideas of determinism and predictability. Introduced in 1927 by Werner Heisenberg, the principle asserts that certain pairs of properties of particles, such as position and momentum, cannot be simultaneously measured with perfect precision. The more accurately one of these properties is measured, the less precisely the other can be known. This principle was not simply a theoretical notion, but a profound insight that reshaped the way scientists understood the behavior of matter at the quantum level. The first key aspect of Heisenberg's uncertainty principle is its challenge to the classical view of determinism. Classical physics, which had long dominated scientific thought, was based on the idea that the universe operates like a machine, with predictable laws governing all matter. According to this deterministic view, if we knew the position, velocity, and other relevant properties of an object, we could predict its future state with absolute certainty. This view, largely derived from Newtonian mechanics, saw the universe as a system in which, if you had complete knowledge of the current conditions, you could compute the future precisely. However, Heisenberg's principle demonstrated that this was not true at the quantum level. It introduced the idea that, at the microscopic scale, uncertainty reigns, making predictions not about precise events but about probabilities. The second key consequence of the uncertainty principle is its implications for measurement in quantum mechanics. In classical physics, measurement was viewed as an external, passive act. The observer, according to classical thought, could measure the properties of a system without altering those properties. However, in the quantum realm, the situation is very different. Heisenberg's principle revealed that measurement itself affects the system being measured. For example, if we try to measure the position of a particle very precisely, we disturb its momentum, and vice versa. This is not a flaw in our measuring devices, but an intrinsic feature of quantum systems. The more precisely one property is measured, the greater the uncertainty in the other. This concept challenges the classical assumption of an objective, passive observer and highlights the active role that measurement plays in the quantum world. A third key point involves the philosophical implications of the uncertainty principle. Classical physics was rooted in the belief that reality was objective, independent of the observer. Scientists believed that the universe existed with defined properties, regardless of whether anyone was there to observe it. However, the uncertainty principle introduced a different view. It suggested that the properties of particles, such as position and momentum, are not fixed until they are measured. The act of observation itself affects the state of the system. This leads to a profound philosophical question. Is reality truly objective, or does it depend in some way on the observer? This was a fundamental shift in our understanding of reality, as it implied that the universe does not exist in a definitive, unchanging state, but instead is in a state of potential until it is observed. The fourth significant impact of Heisenberg's principle is the challenge it posed to the concept of causality. In classical physics, events were governed by cause and effect. If you knew the current state of a system, you could predict its future state through causal relationships. This deterministic worldview relied on the idea that the future was entirely determined by the present, and there was no room for randomness. The uncertainty principle, however, introduced a probabilistic framework where the behavior of particles was governed by likelihoods, not certainties. The uncertainty in position and momentum meant that particles could not be fully predicted, and instead, the future behavior of a system could only be described in terms of probabilities. This departure from a deterministic worldview opened up questions about the true nature of causality and whether the universe operates in ways that are inherently random at its most fundamental level. Another crucial consequence of the uncertainty principle is its influence on the development of quantum mechanics and its applications in modern technology. The principle played a foundational role in the establishment of quantum mechanics, a field that describes the behavior of particles at the atomic and subatomic levels. This was a shift from the classical mechanics that had previously been applied to explain the behavior of larger objects. Quantum mechanics, with its inherent uncertainty, provided a more accurate framework for understanding atomic behavior and interactions. This shift in understanding has had a direct impact on technology. Quantum mechanics is the foundation for technologies such as semiconductors, lasers, and MRI scanners, all of which rely on principles derived from the uncertainty principle. Quantum computing, which utilizes the unique properties of quantum systems, promises to revolutionize computing by solving complex problems that classical computers cannot. Finally, the uncertainty principle has profound implications for the limits of human knowledge. Before Heisenberg's work, there was an assumption that with enough information, humans could understand and predict everything about the universe. The principle challenged this assumption, showing that there are fundamental limits to what can be known. No matter how advanced our technology becomes, there will always be inherent uncertainty when dealing with quantum systems. This limitation on human knowledge raises important questions about the nature of scientific inquiry and the ultimate limits of understanding. It suggests that our quest for knowledge may never reach a complete deterministic understanding of the universe, especially at the quantum level. In conclusion, Heisenberg's uncertainty principle has had a profound and far-reaching impact on science, philosophy, and technology. By challenging the deterministic worldview of classical physics, it introduced the concept of inherent uncertainty at the quantum level. The principle has reshaped our understanding of measurement, the role of the observer, and the very nature of reality itself. It has also paved the way for groundbreaking technologies that rely on the probabilistic nature of quantum systems, from semiconductors to quantum computing. Ultimately, the uncertainty principle reminds us of the limits of human knowledge, suggesting that uncertainty is not just an obstacle to be overcome, but an intrinsic feature of the universe itself. The uncertainty principle, proposed by Werner Heisenberg in 1927, is one of the fundamental concepts in quantum mechanics that dramatically altered the landscape of physics. This principle asserts that there are inherent limits to how precisely we can measure certain pairs of physical properties of a particle, most notably position and momentum. The more accurately one of these properties is measured, the less precisely the other can be known. This principle, which is not due to imperfections in measurement tools but is a fundamental characteristic of nature, challenges the deterministic view of the universe that had dominated classical physics for centuries. The uncertainty principle introduced the concept that, at the quantum level, the universe behaves probabilistically rather than deterministically. One of the key implications of the uncertainty principle is that it challenges the classical deterministic worldview. Classical mechanics, based on the works of Isaac Newton, proposed that if we had perfect knowledge of a system's position, velocity, and other properties, we could predict its future state with absolute certainty. This deterministic view implied that the universe functioned like a giant machine, where every event was predictable and governed by fixed laws. However, the uncertainty principle revealed that this level of certainty is impossible at the atomic and subatomic level. Instead, At the quantum level, particles do not follow precise, predictable paths, but instead behave according to probabilities. The idea that particles exist in a state of probability rather than certainty fundamentally challenged the deterministic view of the universe and paved the way for quantum mechanics, where the future behavior of particles can only be described in terms of likelihoods. The second key point revolves around the nature of measurement itself in quantum mechanics. In classical physics, measurements were assumed to be external and independent of the system being measured. If you measured the position of a moving object, it did not affect its velocity or future state. However, the uncertainty principle highlights the intrinsic relationship between the act of measurement and the properties of the system being observed. When measuring the position of a particle with high precision, the uncertainty in its momentum increases. Conversely, if momentum is measured precisely, the uncertainty in position grows. This concept challenges the classical idea of an objective observer. In quantum mechanics, the act of measuring a system is not passive but actively influences the system, making the observer an integral part of the experiment. A third key impact of Heisenberg's uncertainty principle is its philosophical implications for the nature of reality. Classical physics was built on the assumption that there was an objective reality that existed independently of the observer. It was thought that the universe operated according to fixed laws, regardless of human observation or measurement. However, the uncertainty principle raises the question of whether reality is truly independent of observation. In quantum mechanics, particles do not have definite properties until they are observed. Instead, they exist in a superposition of possible states, and only when a measurement is made do they assume a definite state. This implies that reality at the quantum level is not fixed, but is shaped by the act of observation itself. This idea challenges the classical notion of an objective reality and suggests that the universe may not exist in a definite state independent of observation. The fourth key concept tied to the uncertainty principle is the idea that randomness and probability are intrinsic to the quantum world. Before Heisenberg's work, science was dominated by the belief that if we had enough information, we could predict the behavior of any system with certainty. In classical mechanics, determinism was a cornerstone. Knowing the current state of a system allowed us to predict its future behavior. However, the uncertainty principle showed that, at the quantum level, randomness is a fundamental aspect of reality. This probabilistic nature of particles means that while we can predict the likelihood of finding a particle in a particular state, we cannot predict its exact state with certainty. This departure from the classical deterministic model has profound implications for how we understand the universe and our ability to predict the future. Another key element of the uncertainty principle is its effect on the relationship between position and momentum in quantum systems. Heisenberg demonstrated that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This inverse relationship is not a consequence of measurement error or technological limitations, but is an inherent property of quantum systems. In classical physics, position and momentum were thought to be independent properties, and knowing one did not affect the measurement of the other. However, in quantum mechanics, the principle suggests a fundamental limit to how much information can be known about these properties at the same time. This challenges our classical intuitions and introduces a level of uncertainty into the fundamental building blocks of matter. The sixth key point is the uncertainty principle's role in the development of quantum mechanics as a whole. The principle was central to the formulation of quantum mechanics, a field that describes the behavior of particles at the atomic and subatomic levels. Quantum mechanics differs significantly from classical mechanics in that it describes systems in terms of probabilities rather than certainties. The uncertainty principle is one of the foundational pillars of this probabilistic framework. It helped shape other aspects of quantum theory, such as wave-particle duality and the concept of wave functions, which describe the probability distributions of particles. These ideas are essential to understanding phenomena like electron orbitals in atoms and the behavior of particles in quantum fields. Finally, the uncertainty principle has profound implications for technology. While it initially seemed like an abstract concept, it has practical applications that have shaped modern technology. Quantum mechanics, and specifically the uncertainty principle, is the basis for numerous technologies that rely on quantum effects. Semiconductors, lasers, and magnetic resonance imaging, MRI, all depend on principles derived from quantum mechanics. Quantum computing, which exploits the probabilistic nature of quantum states, is another area where the uncertainty principle plays a key role. Unlike classical computers that process bits as 0 seconds or 1 second, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously. This allows quantum computers to solve complex problems much faster than classical computers. The uncertainty principle, with its inherent randomness and probabilistic behavior of particles, is integral to the functioning of these technologies, revolutionizing fields like cryptography, artificial intelligence, and data processing. In conclusion, Heisenberg's uncertainty principle is one of the most profound and transformative concepts in modern physics. By challenging the deterministic worldview of classical physics, it revealed the inherent uncertainty in quantum systems, introducing probability and randomness as fundamental aspects of reality. The principle also reshaped our understanding of measurement, the observer's role, and the nature of reality itself, raising philosophical questions that continue to intrigue scientists and philosophers alike. The uncertainty principle has been central to the development of quantum mechanics and has led to technological innovations that have reshaped the modern world, from semiconductors to quantum computing. Despite its abstract nature, the uncertainty principle remains a cornerstone of quantum theory, influencing both scientific thought and technological progress in profound ways.